Okay. Welcome everyone to the fourth lecture in this QIT Advanced Topics course. I hope all of you are doing fine. Today's lecture is going to be, I would say, a more descriptive and a lecture in which we will spend more time talking about the philosophy of the topics rather than getting into a lot of technical details. So the pace of it will be slightly different to the ones from before. So let's begin with some sort of recap of what we've done so far, particularly in the last couple of lectures. So in the last lecture, we had two ways in which we arrived at the Gibbs state. So when we began the course, we described the Gibbs state. We based the concept of virtual temperatures upon the concept of Gibbs state, but we didn't really justify where it comes from. And in the last lecture, we had two ways of arriving at this. One of the ways was passivity, wherein we define the concept of ergotropy, the amount of work one can extract from a quantum state by applying a unitary operation on it. And we found that if we were allowed to apply unitary operations on multiple copies of a quantum state, then the only state that does not allow us to extract any work, regardless of how many ever copies we act upon, is the Gibbs state. So this places it in a very special place in that respect thermodynamically. The other manner of arriving at the Gibbs state was the information theoretic manner. We discussed Jane's principle, which was the principle that if we have partial knowledge about a quantum system, then the best possible or the most appropriate state to assign to that quantum system, given a certain amount of information, would be the one that uses precisely that amount of information, but no more, which means that it should maximize the entropy given the information we already have about it. And in the case of thermodynamics, where the total energy is a constraint typically for us, just by the first law that the total energy of the universe or of a closed system must remain conserved, we found that if we associate a system with a particular fixed energy, or rather average energy, but we know nothing more about the system, then the state that maximizes the entropy given this constraint is again the Gibbs state. And so we have these two descriptions, but these two descriptions are both abstract and static in the sense that in our daily life, we have a very different experience of the concept of a thermal state, which are two things. First of all, if we have a system that has been lying around in equilibrium with an environment for a while, we have this understanding that when we pick up the system and we look at its properties, the properties that we assign to it are the properties of a thermal state. The other thing that we know is the concept of equilibration, which is that if we have a system and we allow it to interact with a particular environment, then given enough time, it reaches an equilibrium with this environment, which means that it stops exchanging energy anymore. And the Zeroth Law of Thermodynamics, on which the concept of temperature is based, is essentially, it's based on this concept of equilibrium. That is, if I have a system A, which is in equilibrium with a system B, so I have A in equilibrium with B and B in equilibrium with C, we then state that A must be in equilibrium with C, which is that if we bring A and C together, they will also not exchange energy. And this is really the basis of the notion of temperature. So the two methods that we discussed so far, passivity and Jane's principle, are static, but we really have a dynamic notion of the concept of equilibration and of temperature that comes from our experience of physical systems actually being in thermal states when we interact with them. And so this is the first thing that we are going to discuss in this lecture, the two notions of typicality and of equilibration. So typicality is a statement that when we pick up a particular state, a typical state as part of an ensemble, an interacting ensemble, we see that it is typically in the canonical state or the thermal state. We will discuss what this means more precisely in a bit. And equilibration is the concept that if we leave a system, allowing it to interact with an environment for a sufficiently long time, then it will appear after a while to just be in a canonical state or a thermal state. Okay, So we start with the concept of typicality. Now, the first thing to say about the concept of typicality is that typicality in classical mechanics and in quantum mechanics takes on different forms. This is actually one of the advantages of quantum mechanics. In classical mechanics, if we have a system, for instance, the particles in a gas, for example, then we can describe the state of the system as living in some classical phase space where I plot all of the positions and momenta, for example, of the gas. In order to arrive at a statistical description of the state of a system, I really have to lose information in the classical case. Because in the classical case, if I know the full description of the state of a system, then I know the full description of any subsystem in that. If I know the complete description of the particles in a gas, that implies, just by construction, that I know the state of every single particle in that gas. So classically, a pure global state results in pure states of subsystems. In order to get statistical descriptions of subsystems, I really have to start by losing information on the global state. So for example, I assume that the classical state globally is also a mixture of states, and then I will find a corresponding mixture on the states of subsystems. But quantum mechanically, this is not true. Oops, sorry. Because we can have a pure global state and still have local mixed states because of the nature of entanglement. So if I have an entangled state, for example, a typical 5+, I hope I've chosen the correct one. So 0, 0 plus 1, 1 over square root of 2 on AB. This implies rho A, and the same thing for B is equal to the mixture of the basis states, or rather the maximally mixed state. And so one of the big progresses that was made in understanding the notion of typicality was when researchers discovered that in quantum mechanics, we can derive the notion of typicality without needing to lose information about the global state. So this is what we're going to discuss now, which is a result that goes back to 2006 by Pescu, Short, and Winter. Okay, so let me introduce the scenario, which is the following. So what we consider is we have a global Hilbert space that can be factorized as a Hilbert space of a system and a Hilbert space of the environment. So schematically, something like this. So you have a system, you have an environment. And in this system and environment, you start in a state psi that belongs to a restricted Hilbert space, HR, which is a subspace of HS tensor HE. So for example, we could have a global state of the system and environment, but we say that we start in a restricted subspace corresponding to a particular energy of the state. So for example, I fix the energy of the state to be a certain amount, and then I only consider those states in the Hilbert space that satisfy the constraint that the energy of that state is given by that amount. So this becomes a subspace by definition, as long as it's a linear constraint, so it will be a subspace. Now, in the classical notion of typicality, what one would consider is we could consider the state, the maximally mixed state in this subspace. So this is sort of let's say the canonical principle, which is that you say we belong to a restricted subspace. So let me consider that I know nothing more. I take an equal mixture of all of the states in the subspace. So I pick a basis for the subspace and I take an equal mixture of that. And then I consider the state sigma s, which is the trace over the environment of the maximally mixed, or the canonical, the mixed state in this restricted subspace. And this is the canonical state. So to recap, the canonical state is one where I have a system. I know that the global state of the system environment satisfies some constraint. And so I say the state of the system must be the maximally mixed state over all of the states of the system environment that satisfy this constraint. So this is actually quite similar to Jane's principle, because if HR was fixed energy, then one of the results of statistical mechanics is that sigma s then becomes a Gibbs state, e to the minus beta hs upon z. This is under a few assumptions on the interaction between the system environment, which I will discuss further. But yeah, this is one of the sort of classical typicality and arguments to reach the canonical state. But the big advantage of doing this in quantum mechanics, and this is what was shown in this paper, is that in fact, imagine that instead of picking epsilon r, you actually pick some random pure state in this subspace. The result of that paper was to show that in fact, psi for most states is, or rather, sorry, not psi, but this is psi of the system and environment. But if you take the trace of this over the environment of this psi, which is of course equal to a state on the system, this is actually approximately equal to the canonical state for most states psi. So this is a very powerful result. It says that we do not actually need to assume that we start in a state that is completely mixed on the system and environment in order to conclude that the state of the system is the canonical state. In fact, if you just pick a random state of the system environment, a random pure state, you will still see that the state of the system is approximately the canonical state. Now, of course, this at first glance sounds very surprising. It depends on a certain number of things. So it depends on the dimension of the system being much smaller than the effective dimension of the environment. And it depends on the dimension of the restricted subspace being much larger than 1, and much larger than the error that we will discuss in a moment. So let me now give you the final statement, and then I will discuss what these quantities are in more detail. So I pick a state phi belonging to this subspace R, and this is random. And we have that the probability that the trace norm rho minus sigma s 1, and this of course is trace over the environment of phi, the probability that this is less than a eta prime, and this eta is equal to epsilon plus the square root of ds by d effective. Of the environment, and this eta prime is equal to 2e to the minus c dr epsilon squared. Okay, now the first thing to say is d effective of epsilon is equal to trace, 1 upon the trace of omega E squared, where omega E is given by the trace of this maximally mixed state across the restricted subspace, where I trace out the system. Now, what is the meaning of this effective dimension? So the easiest way to understand this is to look at the cases. So if omega E is a pure state, then of course we know that trace of omega E squared, so the trace of the density matrix squared, is a measure of the purity of the state. This will be equal to 1 for a pure state, and that will mean that D effective of epsilon is 1, of the environment is 1. So this is to say that no matter what the dimension of the Hilbert space is, if you pick a pure state, the effective dimension of that state is going to be 1. If omega E, let's say, is maximally mixed among, let's pick n states. So omega E is 1 upon square root of n, sorry, not 1 upon square root of n, 1 upon n, the sum from I is equal to 1 to n of some states vi, where vi belongs to the Hilbert space of the environment, then you can check that trace of omega squared E is equal to n, because this is a matrix with 1 over n squared, 1 over n squared everywhere. Oh, sorry. Which means that the trace of omega E squared is 1 over n, which implies that the effective dimension of the environment is equal to n. So in some sense, the effective dimension of the environment is the support of the state of the system and the environment on the subspace of the environment, given that you live in this restricted space, which might correspond to fixed energy or fixed any other constraint. Okay, so the first thing that we see is that we want this to be large because we require, so we know that, so we want two things to be the case. We want eta to be small, so that our statement says that the probability of this, the distance between our state rho and just the state, the canonical state that you would get if you started by just mixing everything, is very small. And you want eta prime to be small. So you want that probability, you want the distance to be small, and you want the probability that you are within that small distance as well to be very large. So, oh, I apologize. I clearly have made a mistake here, which is that this is larger. Yeah, this is very important. So you want rho to be very close to sigma, to omega, sorry. And so you want to choose that, you want to find the probability that that is not the case. So the probability that your state is further away from the canonical state by a certain amount, you want to limit that probability. So you want both of these numbers to be very small, and both of them depend on the effective dimension of the environment. As you can see, if this is larger, much larger than, sorry, is there a question?
Yes, I have a question.
Yes, go on.
So the effective dimension of the environment is going to be relative to the system that we choose, right? Or
yes.
the ER that we choose.
Yes.
Okay.
Very much so. Yes, indeed. So one of the, this is a very good question. The point about typicality is that if, for example, we chose the system to be the entirety of the space that we're considering, so there was no environment, there's just a system, then of course, if we start with a pure state, we know the system is just in the pure state. So typicality is not going to work. We're never going to get the canonical state. So the typicality only works where we have a global Hilbert space and we pick a small amount of it that we are actually looking at. So this is the notion of typicality. This is the same way as saying that if I pick, so let's say I pick a gas, a collection of particles in a gas, then if I pick the state to be the full state of the gas, then I just know all of the positions and momenta. So there is no notion of a canonical state or a Gibbs distribution. But if I choose to pick a certain subset, so I put labels on each of the particles of the gas, and I say out of these 1,000 particles that are around, I only follow these 10, and I ask to what is the given a state on a pure state on the gas, what is the state I can expect on these 10 particles, then I come to the notion of typicality, because the distribution on just those 10 particles is the one that will typically be as if I started in a canonical state. So yes, it very much depends on how we split the system and environment.
Sorry, but it depends on how we split the system and the environment, and also the subset R that we pick.
Yes, absolutely, indeed. Because yes, because if okay, so I would say there are two necessary conditions to get to typicality. One is making sure that the system is a small part of the environment, and the other is to make sure that the restricted subspace is not too small. Because, for instance, I could pick the restricted subspace such that it just picks one single pure state of the system and environment. So, indeed, the dual condition is that HR should not be too much of a restriction on the global space of the system and environment.
And if that's so, why do we always pick all the system and all the environment?
Sorry, why do we pick?
Why wouldn't we pick all the system and all the environment as R?
Aha, that is because in some cases you know more than you have more information about the system environment. So, for example, I could have a collection of particles in a gas, and I happen to know the total energy, the internal energy of that gas. So then it just makes sense that the state of the gas is not actually an arbitrary pure state. It's a state that has the energy that I know already. Yeah.
Okay. Yeah. Thank you.
Yeah. Yeah. So in a thermodynamic sense, you can consider you can consider HR to correspond to, let's say, macroscopic observables. So, for example, energy or pressure or volume is a macroscopic observable, although volume is typically fixed right in the beginning so that you can define the Hilbert space. But these are the observables. So you know something, but it doesn't really tell you microscopically anything about the state.
Then we don't have to have that the environment is in thermal equilibrium per se, right? That's part of the.
Indeed, you do not have to have that. Indeed. Nice. Okay. So this makes this so the power in this argument is that it does not start from any notion of equilibrium. You just have a global Hilbert space. You're in some pure state of that Hilbert space, and now you ask the question: what do I expect to see on the state of a subsystem? And what we see is that it looks as if it ended up in it's the notion of typicality says that you could start from the canonical state. That is, you could start from this and define a state of the system, which is your canonical state. But the quantum notion of typicality says you can also start from any psi, which is in a pure state in this subspace, and you will end up with the fact that the trace of that, which is your state of your system, is in fact approximately equal to that canonical state anyway. So yeah, you don't have to begin with a pure state yet, or a thermal or an equilibrium state. Sorry. Okay, so the first thing to explain was, yes, the notion of the effective dimension of the environment. So let me go back to. Yes, so you have the effective dimension of the environment, and well, so the other thing to say is that this this constant C is just a number here. For reference, it's apparently 18 by 1/18 pi cubed. So that's essentially just a number. So we see that eta and eta prime will both be small when the following conditions are satisfied, which is d effective of the environment should be much larger than ds, and dr times epsilon squared, whatever epsilon you pick. So remember, the typicality condition here is sort of a adjustable condition. I can ask, what is the probability of being 0.01 close in trace norm or 0.001 close in trace norm? And I will get different probabilities. And for whatever epsilon I pick, I want this to be much larger than, well, C times this to be much larger than 1, so that this number is exponentially small. Okay, are there any questions at the moment? I guess not, because we've already had questions. Okay, so this is a very basic result. The paper fine-tunes this in greater detail, the one that I've mentioned at the top by Professor Short and Winter, and discusses various different different cases. So one of the cases that's very important to us is if, as I said, if you define the restriction of the subspace to be that of fixed energy. So you start by saying the Hilbert space that we deal with is the one where all the states are exactly one particular energy. Then it turns out you can do this calculation. This is classical thermodynamics, that the maximally mixed state in that subspace has the property that the system looks like it's in a Gibbs state. So at the end of this, what we get is the result that when we have a typical state of a subsystem of a big enough global system is actually the same as if we started in a canonical state. So that concludes typicality. But now we go one step further.
Sorry for the question.
Yes, go on. Please do.
But then if we're talking that we're gonna have a pure state of the bigger system R, then and it has a sufficient enough dimension, like a really big dimension, then like when does this, like I would suppose that having, for example, a pure state with 100 or 1,000 degrees or more degrees of freedom, like starts to, you know, like can we achieve those types of quantum systems? Like don't we tend to have like decoherence and go back to a classical state? Or I don't know if it's not related to that.
Aha. Yes, so I would answer the question in two ways. The first one is to say, yes, if you have a system with a high enough degree of freedom, then eventually you have decoherence and you end up with mixed states anyway, which in fact makes typicality even easier, because if this statement that we just derived holds true for a pure state, then if you mix pure states together, it's going to continue to hold true. However, the second way I would answer it is to say that even when you consider the notion of decoherence, when you say that a state is decohered, what you mean is that it has gotten correlated with some environment that you have no access to. So you can always still step back and say, well, imagine now I still go to the state of the system that I'm considering, as well as the environment that it interacted with, and make the statement there that even if I did, so typicality is stronger. It says, even if I considered the non-decohered state, I had access to environment, and I considered a pure state of the system and the environment in total, I would still see that the state of the system would typically look like the canonical state. So in terms of the description of systems, when you don't have access to an environment, what you said is correct. But even if you do have access to the environment, you still have this the statement that the state looks like a typical canonical state.
Thank you.
Yes. Okay, so the next thing we talk about briefly is the notion of equilibration, which is slightly stronger, because so typicality is it's still a static description. It's if I just pick a state, then what does it look like? Equilibration talks about what a state goes into. So I have the same setup now, and I'm going to switch. I'm going to switch notation a little bit, just because I'm following the notation of the papers for this lecture. So I call the rest, instead of calling it environment, I call it a bath. So I start with the assumption that I have a system, I have a bath, and I have a Hamiltonian, HSP. It's the Hamiltonian of the system and the bath. And it has the property that there are no degenerate energy gaps. Now, why is this? What is the influence of this assumption? So the no degenerate energy gaps is kind of interesting. Consider the following. Imagine that I just had two, let's say 2 qubits, for example, one at We've done this many times before. The joint system then looks something like this. So you have 0, EA, oh, sorry, EA, EB, and EA plus EB. And immediately it's immediately clear that this gap here is, of course, EB, which is the same as this gap over here. And the reason for this is because HAB is the sum, HA tensor IB plus IA tensor HB. So a very simple thing that you see is that if I have a Hilbert space, and this is very easily generalizable, if I have a Hilbert space that splits into the tensor product of two Hilbert spaces in such a manner that the Hamiltonian is just the sum of the individual Hamiltonians, and there is no interaction term, this is important, then I will immediately, as a consequence, have degenerate gaps, because every energy gap in one of the systems will appear in the joint state as many times as there are states in the other system that you have done the tensor product with. So in this case, it was twofold repetition because each of them are qubits, but in a more complicated state, you'll have many, many more of these. So for example, if I made the extra Hamiltonian, for instance, I could add, and this is a Hamiltonian that we will in fact revisit at some point, plus 1001. This is now a Hamiltonian that influences these two states, because these two states are no longer eigenstates of this Hamiltonian. What you get in the end is then you get the state phi plus, which is 0, psi plus. The new states, eigenstates of the Hamiltonian, are the states 0, 1 plus 1, 0 by root 2, and psi minus, which is 0, 1 minus 1, 0 by root 2. And the energy, and these two energy levels, they don't actually stay there. They sort of move slightly downwards or upwards, or vice versa, depending on the value of G and stuff. So what you get is that the degeneracy in the energy gap, so this is not a degeneracy in the actual level, but it's the equality in different energy gaps gets broken when you put in an interaction term. So this is another way of saying that if you have no degenerate energy gaps, it is impossible then to have non-interacting components. Yeah, and the reason for this is because what we're going to discuss now, equilibration, is the notion that if we have a system and it's in contact with the environment, eventually the state of the system is going to go to the canonical state that we just talked about previously. But of course, we know that one easy way to make sure this doesn't happen is to have the system isolated from the environment. So we need to prevent this, and this is one mathematical way of preventing it. Now, this is not a necessary condition. You could consider relaxing this condition and having other ways of ensuring that your system interacts with the bath, but this is a sufficient condition because it simply eliminates the possibility that the system is not interacting with the bath. Any question here? Okay, so the next two things that I will discuss is the time average state. So I'm going to say omega S. So it's the time average state. So what we do is we start from a rho S t is equal to 0, and then we propagate it in time, and omega S is equal to the limit 1 upon tau of the integral of 0 to tau of rho S of t dt. Oh, sorry, tau goes to infinity. So this is to say you have a state of a system and I allow it to keep evolving and I look at the average of the state in time. So if you did not have equilibration, the time average state would still exist. So for instance, if you have a state of a harmonic oscillator, for instance, or just a spring, you can define the time average state and you get a very well-defined answer. But what you have is that the actual state of the system keeps oscillating away from this time average state, and the distance of that state from the time average state will be something that doesn't go to 0. equilibration is the property that this distance, and this distance we will take to be the trace norm again. So the one norm of rho s and omega s is approximately 0 for most times t. Okay? So this is the thing that we're trying to sort of prove. Okay, so the statement that this paper is able to derive is to say that this distance d between rho s t omega s and this averaged over time is upper bounded by something we've already seen before, which is ds upon d effective of omega of the path. And this in turn is also upper bounded by ds squared d effective of omega. So,
sorry,
yes?
what do you mean by for most times t?
So that's what I'm going to say now. So let me give you, but it's a good question. So let me give you an example. Imagine that I have let's say the position of a spring, so of a harmonic oscillator. So I have x is equal to a cos of t. Then and then what I will have is that if I consider the state to just be the position, so this is an example here, then omega is equal to, well, 0, because this is the 1 over tau integral of a cos t dt 0 tau, limit tau goes to infinity. This is equal to 0 because it's a sinusoidal such cos function, so it's going to average out to 0. But now if I do the trace norm in this case, so if I say what is x minus omega x, the one norm, this is just the absolute value of the difference between x and that. So this is going to be a times the absolute value of, oh, actually I don't need the norm thing here, the absolute value of cos of t. But now the average of this term, x minus omega, average over time. So I can average over any amount of time. So let's say average over tau, I say 1 over tau times integral of a cos t dt 0 to tau. This is not equal to 0. And what this is to say is that even though the time average is well defined, the state oscillates away from the time average to a sufficient distance such that when I take the average amount of the distance, and the distance, remember, is always positive, then I get something that is not 0. But if I had that, in fact, I have another situation and I have some other state and it's described by y, and I have that y minus omega y, the average over time goes to 0 when I take the averaging time period to go towards infinity. This basically implies, because remember I'm summing up all of the distances to get the average. But if all of this average goes to 0, that means that that distance itself must also tend towards 0 in the long run. Because if this doesn't tend towards 0, if it, for example, converges to a particular constant, then that constant is what I will get from the average. So the statement is, if I know that this average of the distance tends towards 0, that means for most times, that distance itself must be 0. The set of times over which it is actually a finite distance away from 0 must be much, well, of measure 0 compared to the rest of the times when it's actually at that average. Does this make sense? Forgot who asked the question. But all right.
It makes sense, the thing you're saying about the measure, but I don't see how in this example. So you're not talking about any specific function. It's just like for a given function y, we would have this property.
Yes. So
Yeah.
if you have that the average of the distance of y from omega goes to 0, then it follows this. This is something that I wouldn't prove now, but it follows then from this statement that y is approximately omega y most times t.
Okay.
Because,
okay. Yeah.
Yeah. Because another way of seeing this is that if you plot, let's say if you plot y minus omega, or sorry, not the average, but the one norm versus time, then this is something. This is some function that is sort of, and this must be very close to 0. Otherwise, the average is not going to be
Okay.
close to 0. Yeah.
Yes, yes.
So an example of this, just to complete this, is I would just take a cos t times e to the minus t, for example. So it's a cost function that is also decaying towards 0. So this is an example. It still continues to oscillate, but you can see that it gets closer and closer to the state.
Okay. Thank you.
Okay. So yeah. So in this case here, the result is as follows. The average of this distance, which, as we've now discussed, is also a measure of how long it spends away from this canonical state, is again bounded by a similar expression that we had before. And remember, the effective of omega of the bath is equal to, again, 1 upon trace of omega squared of the bath, and omega of the bath is the time average state, is 1 upon tau, integral 0 to tau, rho of the bath is a function of t, dt. Okay. So this is now different from typicality, because in typicality, we said we start with the pure state of the global system, and then we see for average pure state that we pick, the subsystem appears to be in a canonical state. But here I go in a different way. I say I start in a system. I start with the state of the system that can be anything. So in particular, I can pick it not to be the canonical state. I can pick it to be a very pure state. And then I allow time to run and I ask, what is the sort of state that this system looks to be in over a long period of time? And I get that as long as it's interacting with the rest of the environment, which is the reason why we had the non-degenerate energy gap constraint, it will follow that this system looks as close as possible to the time average state. And the other result that is part of the typicality and equilibration, part of these two papers, is that time average state is then once again the state that we derive from the canonical ensemble that we discussed in the equilibration part. Okay. Yes, so these two things together, typicality plus equilibration, sort of mean that we can take states to be in the canonical ensemble for most purposes. Now, I actually want to stress for most purposes, because when we talk about thermodynamics, typically what we're doing is we have a system and we make measurements or transformations on them that are not very fine-tuned. So for instance, on a gas, if we use a gas to do work, we make the gas push against a piston, for instance, but this doesn't depend on the individual motion of the particles in the gas. It only depends on pressure and the structure of the piston, for example. So when I say most purposes, I mean most observables that we measure that are not extraordinarily fine-tuned will look at the state and treat the state as if, or have the same result for those transformation or measurements as if the state was in a canonical ensemble. You can always, of course, pick something that is fine-tuned enough such that this breaks down. This is the same in classical thermodynamics. So this is why you have such sort of intricate results corresponding to our intuition. Yes, it is the case that typicality and equilibration holds, but you have to define exactly your assumptions on which they are based very carefully, because you can always go outside the set of assumptions and then you will go away from sort of a thermodynamic sort of treatment of the system. Okay, all of this is to come to the conclusion, really, that the canonical state is something that's very well justified as a state that forms the basis of thermodynamic theory. And of course, the most typical canonical state, common case, is that HR corresponds to this restricted subspace that we live in, is the one of fixed energy, or fixed total energy, rather, between the system and the environment, which then leads to the Gibbs state. Rho s is e to the minus beta times the Hamiltonian s upon z. The final thing that I briefly touched upon before, and that I mention now again, is that this assumption, so this assumes HS tensor identity on the path plus identity on S tensor H on the path plus some interaction Hamiltonian on the system and path. And we need that this interaction Hamiltonian is much smaller than the Hamiltonian of the system. So the energy that is involved in this interaction is much smaller than the energy of the system or the energy of the environment, but in particular the energy of the system. And the reason for this is that the Gibbs state is based on the temperature of, or it's rather, it's based on the Hamiltonian of the system, but the Hamiltonian of the system is not going to look like the Hamiltonian of the system if it's strongly interacting with an external system, with the external environment. So in order to have isolated systems on which you can define temperature, it requires that the interaction between the system and the environment is small enough that it doesn't actually change the energy scale of the system itself. So this is the final sort of assumption behind the Gibbs state. This is also sometimes known as the weak coupling regime. And there is, of course, a lot of thermodynamics that is done in regimes where this is not true. So for example, you can have a spin chain where the interactions are very strong in between each member of the spin, and then you cannot actually deal with Gibbs states. You can deal with canonical states because that's completely general, but you cannot isolate yourself to Gibbs states because they don't make sense in such a regime. All right, this concludes our discussion of typicality and equilibration. I highly recommend the two papers that I just talked about as reading material, because they also discuss the philosophy behind all of these things in more detail than I've gone through in the lecture. Are there any questions before we take a break?
Yes, I have a question.
Go on. Yes.
At some point, you stated a result that comes from one of the papers, and you said that the probability of the difference of our state minus the canonical state was less than, or more than whatever.
Mm-hmm.
But you're taking a probability, so there must be a random variable. And in this case, I think it's the state, but how do you define a state to be a random variable in this case?
Yes. So, so this is something that, okay, I know descriptively, but I would not want to go in technical details because I've not done something myself. So the question is, therefore, if you have a quantum state space, how do you define a measure over that state space? Because you want to sample, in order to have a probability distribution, you need to sample from that measure correctly. So this is called the Har measure, which is something that one can look into. I wouldn't want to say much about it because I haven't worked with it, but just it suffices to say that it defines sort of a justified measure on quantum systems. Yeah. This is all I would say right now because I don't know much about it. I will actually look into it and perhaps I will have a more detailed answer to give you in the next lecture.
Okay. But then if I pick one specific state at the beginning on my on my R Hilbert space, then I can get something not canonical. It's only an average.
Indeed.
Canonical.
Yes, absolutely. So if they are going to be particular states on your Hilbert space of system and environment for which that you will be further away from. So let me go back. So that particular state such that this is true, the distance is greater than eta. But then when you average over all of the states according to this well-justified measure, you do get that the number of states, the fraction of states for which the distance is greater than eta is less than this other eta prime given by these two things. Yeah.
Okay, thank you very much.
You're welcome. Okay, if that is all, then I would say that we take a break now, and we will return to continue speaking at, let's take a bit of a longer break and come back at 4:50. So at 16:50, we continue the lecture. See you soon.
I do have another question. Sorry.
Sure. Yeah. Go on.
You mentioned something like if a Gibbs state is different than a canonical state, and
yes,
like weren't both defined like the exponential of minus beta, the energy over the partition function, or what did I miss? Sorry, I think I got.
Yes. So the Gibbs state is very particular. So the canonical state is a very general statement. So the canonical state is simply defined via this procedure. You have a Hilbert space of system and environment. You have a restricted subspace of that. You define it however you like, as long as it's a valid subspace. You take the maximally mixed state on that subspace, and then the state of the system that you associate is the trace. I mean, it's just the system partial trace of the environment of that maximally mixed state. So that's a canonical state. You have a restricted subspace, you're maximally mixed there, and you take the subsystem state and you define that as a canonical state. The Gibbs state is the particular case where you choose this restriction HR to be that of a fixed energy. So it's a special case of a canonical state. If you choose the restriction to be, I am only in a subspace of energy equal to 10 joules, then you're going to get, then you go through the same procedure, and you see that the system state that you get is the Gibbs state, corresponding to a particular temperature and corresponding to that energy. Does that answer the question?
Yeah, thanks a lot.
Okay. Okay, see you in 12 minutes time. Or is there a question, Floria?
Yes, I would have had a very short question,
Yes.
which might be a bit off topic or too far stretched regarding this result from Popescu and the others. Namely, for example, if we take as the environment, say, the entire universe, and as a system, say, a macroscopic object like a glass of water, and
yes,
can we then also interpret the result in such a way that we don't arrive at this say problem we normally have in quantum mechanics when we try to say why macroscopic objects behave in a non-quantum way? Because here we say that this glass of water, it's a subsystem with many degrees of freedom less than the environment. And I think at some point you said that decoherence means like it's gotten correlated with the environment we don't have access to. And for example, in this case, the environment is so large we do not have access to the full environment. Does that stretch the result too far in a way that I'd say based on this result, I observe the glass of water in a non-quantum way?
So I would say that, okay, there are two things I would say here. So the first thing is you can definitely apply this result. I don't think it's a stretch. In fact, I think that's a good application of it. Take the global Hilbert space to be the Hilbert space of the entire universe. So then there's nothing that is out of access. So then you can't talk about decoherence anymore because you're always in a pure state at the level of the universe. But given this result, you still see that if you pick a small enough subsystem of the universe, and a glass of water definitely qualifies, then it will look like, for most purposes, most of the states that you could pick on average are going to be ones that are canonical states. Now, the question of whether this justifies that's on macroscopic objects to see non-quantum behavior, I think that has to do, it's the juxtaposition of two things. In order to have a system that, even though you start with quantum mechanics, is described essentially classically, you must have that its state, the combination of the state as well as the transformations and the dynamics that you are doing with the state, both of them do not actually use quantum features. So you have to join the typicality result, which is to say an average state that you would pick is typically one that is essentially classical, because it's going to be a canonical state, and these are going to be mixed states in general, with the addition that the observables that you act with on the state are also essentially classical. So I could make, for example, I could make a very strong projective measurement on one single particle in a glass of water, and that is going to take me into the regime of quantum mechanics, because it's going to isolate the wave function. It's going to project the wave function into a tiny wave packet, and now that's going to look like a quantum state rather than a mixed state that it started off with. But if I don't do that, I only restrict myself to weak measurements, which is measurements that do not actually project individual particles into very well-defined eigenstates, then I will end up that it stays sort of effectively quantum. So it's a combination of this as well as ensuring that the observables that you act with on the system are also macroscopic and not projective fine-tuned measurements.
And then this second argument that, say if we measure a system that's essentially has to be carried out through an interaction, and the statement that if I observe, say, this glass of water macroscopically, I'm only weakly interacting with it, and then we don't only use the typicality argument, but also equilibration in the weak interaction regime, or is that?
No, this is something even more. It's not only typicality and equilibration. This is also to say that if I start with a state of the system that is essentially classical, because it doesn't have much quantum coherence, it's a mixed state of many energy eigenstates, then, and I make a measurement upon it, and in general, a measurement which is not a general projective measurement, but a general channel, the final state of the system, whether it's essentially classical or whether it looks quite quantum, is going to depend on how the properties of that measurement. So if that measurement happens to be of a macroscopic observable, then it's not going to be the case. Then a state that starts off essentially classical is going to end up essentially. Excellent. Thank you very much. All right, so let's continue now for the second part of this lecture, which is going to be an introduction to resource theory. So this is something that we will spend, I think, definitely the next lecture and possibly a little bit after that upon, because a lot of recent research in thermodynamics, by recent, I mean, we can cover the last decade or slightly longer, can be put in the form of a resource theory. Okay, so let me say what we mean by resource theory. So resource theory is defined by the following things. We have, so we have a state space. Okay. Then we have a set of allowed states. So we can call them free states. And a set of allowed transformations. And we must have a property. So if I have the set of allowed free states, let me call this these states tau, just because it evokes the thermal state, even though depending on the resource theory, it might not exactly be that. And then I have the set of allowed transformations, which are some general maps on the quantum system. And we must have the property that if I call this tau belonging to, let's say, F, and we call the set of free states F, I must have the property that the allowed transformation acting on any free state is also within F. So I must have that the free states have the property that if I do an allowed transformation, I get back another free state. Any state, any row that is not in the set of the free states is called a resource. Okay, so we already dealt with one example of a theory which we could connect to resource theories, which was a theory of passivity. In the case of passivity, what we had was there we in fact we didn't start with a set of free states. We started with a set of allowed transformations. Set of transformations was any unitary operation. And there we defined a currency, which was the ergotropy. So the currency in general is some function of a state rho. And in general, this is greater than 0 and is equal to 0 for the free states. So there's more to say upon currency, but in the case of passivity, we defined ergotropy to be a currency. This was the valuable thing that we wanted to extract from states. And the free states were those that you had 0 ergotropy. In the case of passivity, the free states were passive states. In the case of complete passivity, where remember we had unitary operations which were either single or multi-copy. And in the case of single copy, we got the free states to be passive states. In the case of multi-copy, we got the free states to be general, or the only free states were Gibbs states, which is a subset of the passive states. So in today's lecture, I'm going to introduce another example. So I'm going to talk about different examples in time, but the one that we will introduce today is so-called noisy operations, which is in fact a subset of the resource theory of thermal operations. So let me define both of these at the moment. So noisy operations is based on the following paradigm. We do not work with energy. So here there is no energy. So no Hamiltonians to worry about. All we are worried about, or all we are concerned with, is the information content of different systems. So in noisy operations, the free states are maximally mixed states. And the transformations are unitaries of this form. So if I have a state rho, then under a noisy operation, what I can do is I can take rho. I can let me give more space to this. Take rho, tensor it with any maximally mixed state. Maximally mixed state divided by, so the maximally mixed state on an ancilla. So A is an ancillary system. And then I'm allowed to do any unitary operation I like on this. And then trace out part of the joint state. Now, this is a slight technicality here, a subtlety. This trace is not necessarily equal to the original system. So for example, I could have rho of a qubit. I can tensor it with the maximally mixed state of B. So this is rho A on a qubit, identity over B by 2, identity over C over 2. So I take 3 qubits, and I take a unitary on all three of them, for example. And then I trace out C on this expression to give me a rho prime, which remember is going to be on A and B. But all this is to say, the final system need not belong to the same Hilbert space as the original system. So in a noisy operation, I'm allowed to take a state, allowed to append the maximally mixed state on any Hilbert space, do any unitary operation I like, and then trace out part of that system, part of the global state of the system, but not necessarily the same under the same division that I started off with. Okay, so this is a noisy operation. So if it is the case that A and A prime are the same, then we get noisy operations acting on the same dimension, or even more restricted, on the same Hilbert space. So this is, okay, let me differentiate this. This is all noisy operations. And then we have thermal operations. So here the energy matters. So here we have energy. So in thermal operations, we take a state rho, and we are allowed to tensor it with any state, thermal state tau at beta. Let's say, well, sorry, tau beta of h. I will use this notation, and this is basically tau is e to the minus beta h upon the partition function. I do a unitary on the system and the bath. U dagger. Oh, and then I have squeezed myself in the corner. And then I trace over the bath to get rho prime on the system. So here I will just, for simplicity, stick to the case that we do not change the Hilbert space of the system under thermal operations. But in addition, these unitaries are energy preserving unitaries. And what this means is that, remember, the unitaries on the system and bath. So U on the system and the bath, this is H of the bath, must commute with H system plus H bath, which I can write down in full as the sum of the two Hamiltonians. Okay, so one of the things that I want to discuss now is the fact that resource theories are defined mathematically via free states and allowed transformations, but they have a operational basis in the sense that we have a particular regime in mind when we design a resource theory. So it's kind of like saying the mathematical set of all possible resource theories we could think of is infinite, because there's so many, well, there are infinite number of ways to restrict ourselves in terms of allowed transformations, but only some of them correspond to real physical scenarios that we have. So the scenario of noisy operations is very much an informational, this is a information theoretic scenario. It's basically the case where you are, so for example, in quantum computation, you have different states, you want to transform one into the other, and the only state that you can get for free are states that are not, that are already maximally mixed, of which you have no information at all in the beginning. So this is also a resource theory that is very related to entropy, for instance. Thermal operations have a bit of a different significance. Here, the operational significance is that energy is conserved. So you're allowed to do any unitary transformation, but not one that actually inputs energy or takes away energy from the system. Entropy is also, of course, conserved because you're doing a unitary operation. So the entropy on the system and the bath together is conserved. But remember that because you're dealing with a bath, once you exchange energy with the bath, the entropy of the bath, of course, will change. So when you split the system and the bath separately, there the entropy is not necessarily conserved. Right. There's something else to say here, but it's not at the top of my head at the moment. Yes. Okay. So thermal operations correspond to energy and entropy being conserved. And the final thing is to say that the notion of a thermal bath. So the ideal notion of a thermal bath is that for every H bath, we can pick tau is e to the minus beta H upon Z. So let me sort of divert here a little bit to talk about the notion of a reference temperature. And this is something that comes from our everyday experience. So for instance, the temperature, if we walked outside our apartments right now and went to the outside, the temperature of the air around is sort of a reference temperature for most of the thermodynamic machines we have in our lives. For instance, the whole goal of heating inside of our homes is to increase the temperature inside to be larger than that reference temperature. The whole goal of refrigerators inside of our homes is to decrease the temperature of the inside of the refrigerator to be colder than the temperature outside. Although, of course, if you are in the middle of winter, you might not need to do this, but that's a different consideration. So in every thermodynamic theory, you have as a basis a sort of reference temperature that you consider to be free. So there are many ways of labeling it. Sometimes it is called the reference temperature, or the environment, or the sink, or the room temperature bath. These are different ways to, if you open different research papers, they will be called by one of these different terms. But this basically refers to a temperature or environment which you consider you have for free, that it exists in such a large quantity that you always have access to this temperature. And mathematically, saying that we have a temperature for free is exactly this condition that I've written. It's a condition that if I were to just mathematically pick any particular Hamiltonian at will, this bath, the ideal bath, will be able to spit out to me the thermal state corresponding to its own temperature, the temperature of the bath, and the Hamiltonian that I've picked. So this is the meaning of an ideal thermal bath. It's an object that can give me thermal states of any Hamiltonian that I choose. And so then to recap what thermal operations are, I have a state of a system. I'm allowed any state of the bath. I can pick whatever Hamiltonian I want, however large, the Hilbert space is not bounded. I do a joint unitary that preserves the energy, and then I look at the final state of the system. Okay. So now I've defined these two resource theories. What is the big question about them? So in this case, I have that rho went to a different state. Let me label this as well, equal to rho prime. And so the fundamental questions now that we have, so the questions start with rho, and then you ask the question, can rho go to sigma? So this is a very basic question. If I have a state rho, and I have the set of allowed transformations, can I take the state rho to another state that I pick sigma? Then we can ask the same question. Can sigma go to rho? And then I can ask the question, and this is to do with rates of conversion. If I have n copies of the state rho, then what is the number m such that I can take this into m copies of the state sigma? So it may be possible that a single state rho cannot be transformed into a single state sigma, but in fact, I can transform n copies, like 3 copies of rho into 1 copy of sigma, or there are many versions of this. And then we have the rate of rho going to sigma. And this is the definition of a rate, is equal to this number, this ratio, m over n, in the limit of infinite copies. So basically, if I define this as rho tensored kn goes to sigma tensored km, then in the limit k tends to infinity, this ratio, the ratio that I get, well, sorry, let me put it this way. This is not a good way to write this. Rho tensored n goes to sigma tensored, let's say, f of n. Then the limit n tends to infinity of f of n divided by n is equal to r of rho tends to sigma. And the reason for this is that it's very possible that because of intricacies, when you deal with a finite number, you see some things only asymptotically that you cannot see when you deal with a finite number of copies. And so if you take the limit of this quantity, then you get a sort of rate of convergence. So this is one of the questions that one can ask. Another question that one can ask is the question of monotones. So monotones are functions f of rho and sigma, such that if rho can go to sigma, so if this is possible, then f of rho comma sigma must be greater or equal to 0. So this is basically something to say, if it's possible to transform rho to sigma, then you have that this function, this monotone, must be something that's greater than 0. So it's a manner of classifying the states via monotone. I realize now that an easy example to use to give all of these, to put all of these on a good footing, is what we already dealt with in majorization of vectors. So remember there, the allowed transformations were any doubly stochastic matrix. And what we got is then from this, we concluded that the free state is the maximally mixed distribution. And the reason for this is two things, and these are the two ways of looking at the free state. One is that if you took the maximally mixed distribution, if you did a doubly stochastic matrix acting on V, where V was of the form 1 over D, dot, 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 so the maximally mixed distribution over D dimensions, then this is always equal to V for any doubly stochastic matrix. So this is one of the properties of doubly stochastic matrices. If it acts on a uniform distribution, you get a uniform distribution. Another way of seeing this is that if you pick a state, so let's, okay, this is I should just label this as identity over D, identity over D. If you pick a V that's not equal to identity over D, then there exists a doubly stochastic matrix such that the doubly stochastic matrix acting on V is in fact equal to identity over D. And in fact, this is not, it's not even a difficult procedure to pick such a stochastic matrix. You can pick one that works for all V. It's the one that mixes every element. So for example, pick the doubly stochastic matrix that's equal to, yes, 1 over D in all of its elements. And if you act with that on any vector V, you will get the maximally mixed state, identity over D. So this shows that the free states are the max mixed distributions. But we have more stuff that we can say, because remember, if we had V1 and V2, we knew that V1 can go to V2 via a doubly stochastic matrix D if and only if V1 majorized V2. So majorization was a pre-order on the state space. And given that majorization was a pre-order in the state space, any sure convex or concave function was a monotone. Because we knew if V1 can go to V2, then that implies that V1 majorizes V2, which implies that f of V1 is greater than f of V2, or greater or equal to, if this is sure convex, or f of V1 less than f of V2, if this is sure concave. Okay. So this is, so the theory of doubly stochastic transformation of vectors is a very simple example of a resource theory. We define a state space, which is the state of all classical vectors. We define the allowed operations on the state space, which is the set of, which is a set of doubly stochastic transformations. And then we ask, what are the free states? This is clearly all of the maximally mixed distributions, or only the maximally mixed distributions rather. And then finally, we ask, what are the monotones, which is any function that obeys this preordering among the states. And we know the preordering among the states is majorization, because there's an if and only if condition between majorization and doubly stochastic transformations. So every sure convex and sure concave function then becomes a monotone for the resource theory. Is there any question on this part? No, none so far. Okay. So there is not enough time to go into the resource theories of noisy operations. So what I will do briefly now is to introduce the concept of a Lorenz curve, which is just another way of looking at majorization. And this is the following. So what you do is, so imagine that you have two vectors V1. Let's not say V1 and V2. Let's say A and B. In fact, we can use the old example that we have: 0, 2 over 3, 1 over 3, and B is 1 over 3, 1 over 3, 1 over 3. Okay, so one of the ways of writing this this vector is in the following manner. This is the Lorenz curve that I'm constructing. So I define, so let's just define this as the unit 1. And because the state space is 3-dimensional, I'm going to, like, this is 1 over 3, 1 over 3. And in the first place here, what I do is first I order this. So I get the ordered vector A in decreasing order is 2 over 3, 1 over 3, and 0. The ordered vector B is equal to B. So that's the same as the original vector, 1 over 3, 1 over 3, 1 over 3. And now I do the following. I place here, I place A1 ordered. So let's call this 1, 2 over 3, 1 over 3. Okay. So at this point here, I write A1 ordered. And then at this point here, I write A1 ordered plus A2 ordered. And then finally here, I have A1 ordered plus A2 ordered plus A3 ordered. And then I connect them. So that's that, and that's that.
I have a question. Why do we have in the x-axis 1/3, 1/3, and then 1?
This is just because the dimension is, so I just have to split the x-axis into equal line segments. The length of each line segment is the dimension of the space. Well, it's 1 upon the dimension of the space. Actually, if I'm not mistaken, the division being regular is not actually very important for the purpose of Lorenz curves, but it's just nicer to write down. So all I needed is just 3 points on the x-axis. That would have sufficed. But the y-axis is the one that's important, because these are the probabilities here in the vectors. or the sums of properties?
I think he's referring to why is it 1/3 and then not 2/3? Because you wrote 1/3, 1/3.
Oh, I'm sorry. Yes. Yeah.
Okay, yeah,
Sorry,
no,
I didn't get that.
thank you, Mark.
Yeah. Thank you. Right. And then I do the same thing for B. And for B, I'm going to get, this is B1 ordered. This is B1 ordered plus B2 ordered. And then, of course, it's the same. They're both normalized vectors, B2 ordered plus B3 ordered. And then I connect them. And I haven't drawn this very well because what this should be is a straight line because it's a uniform distribution. So yes, so that's the reason for picking. So if you pick the distances on the x-axis to just be equal distances for every element, then what you get is that the uniform distribution is a straight line from 0, 0 to 1, 1, because every single step on the y-axis is the same as the step on the x-axis. So these two things that I've just drawn, this is called the Lorenz curve of A. Now the Lorenz curve is a property of the ordered vector. So even though A itself is not ordered, the Lorenz curve always orders it first in decreasing order of the elements, and then you construct the curve. Now it's very easy, or it's immediate to see that majorization, which is to say the sum from I is equal to 1 to any k of the ordered elements of A, being greater or equal to the sum I is equal to 1 to k of the same ordered elements of B, is the same as saying the Lorenz curve of A is higher than, or actually probably the way of saying is nowhere lower than that of B. So if I was to parameterize this as some sort of Li of A, which is the each of the points for every I, then this is to say that Li of A is greater or equal to, let me say Lk actually. Lk of A is greater or equal to Lk of B for all k. And I mean, this is, you can see why I've chosen k. It's exactly because the Lorenz curve is constructed out of the partial sums. So it's a very easy geometric way of understanding whether a state majorizes another. Its Lorenz curve must be greater or equal to that at all places. So for instance, we could construct a very simple example of a Lorenz curve that doesn't satisfy this condition by picking, let's say, C1 ordered to be here, C2 ordered to be here, and then the same for the normalized sum. So it would be a curve that is above A at the beginning, but then it's below A later. So then in this case here, you would have that A comma C are not comparable by majorization. So this is a very simple way of understanding majorization geometrically, which will be useful when we talk about the results that we get from the resource theory of noisy operations and the resource theory of thermal operations. Are there any questions?
Yeah, I have a question, but you briefly answered it, I believe, because I was about to ask, is this really useful? Like, can we use this for something?
Yes. So one of the ways it's going to turn out to be useful is that, so I can give you a glimpse of this, which is in the case of noisy operations, remember that we did not have to maintain the Hilbert space of a system. We could start with a two-dimensional state and end with a three-dimensional state, or vice versa. And then sometimes you want to understand whether a state, so for example, imagine that I want to see whether the state 1/3, sorry, no, not, yeah, let me say, so 1, 0, 0, can it be converted into the state 1, 0? Now, both of these states are pure states, and in their own respective ways, they are the extremal points of majorization, because we know that the first state majorizes every one of the 3-dimensional states. The second one majorizes any other 2-dimensional vector. But to know whether the first one can be transformed to the second one by noisy operations, this is not immediately clear. And it turns out that the answer then, and this is something we will discuss probably in the next lecture, is given by writing the Lorenz curves of these two states, because the way I can do this is, even though they are of different dimensions, I sort of shorten the Lorenz curve for both of them to be in the same length. So this is the end of the Lorenz curve. So there's going to be this point, of course, and the first, so I will call this the green one. So the green vector is going to look, because it has 3 elements, I'm going to split this into 3, and I get these 3 points. And this is the Lorenz curve. Whereas the blue, the other one, which I will label the blue vector, this one has 2 points. So I have to split the same distance into 2. And so then I get these 2 points, which gives me this Lorenz curve, that one and that one. So geometrically, it's immediately clear to see that the green Lorenz curve is greater than the blue Lorenz curve, which implies that the green state, the 3-dimensional pure state, can be converted into the 2-dimensional pure state. And this is the more technical way via majorization would be to say that we can take the green state, we can tensor a maximally mixed state, and then we can transform it into the blue state, tensor another maximally mixed state. And on that joint system, the dimensions are the same. So you can then use the theory of majorization. But it's much simpler geometrically to directly just draw these 2 Lorenz curves in the same sort of block of space and see which of the Lorenz curves is higher than the other. So this is why Lorenz curves are useful, because for dimensions not being equal, they immediately allow us to compare stuff.
Okay, this is very interesting. Thank you.
You're welcome. Okay. Yes, so with that, I think we can conclude this lecture. In the next lecture, we will really go into the details of noisy operations and then try and cover, well, noisy operations will be one, and then the other will be the rate of conversion of states in the resource theory of thermal operations, after which I will give you other examples of resource theories to sort of give you an idea of the general paradigms in research in quantum thermodynamics. And with that, we conclude today's lecture. Have a good evening and see you at the next lecture. Thank you.
Thank you.
Bye.
Thank you.